Hi, my name is Jim Bowles, and I'm New Hampshire DOT's District Construction Engineer for the East Central portion of the state. This next presentation encompasses two bridge slides, one done in the fall of 2019 and one in the fall of 2020. The same system was used for sliding both bridges. The presentation is broken up into three sections. First, the why. In other words, other than it seemed like a fun thing to try, why would you do it? Since it was her idea in the first place, here's Jennifer Reczek of the DOT to present this portion of the show.
These bridges are located in Ossipee, New Hampshire, in an area where New Hampshire routes 16 and 25 run concurrently. With a posted speed limit of 45 miles per hour, this roadway carries an average of 11,000 vehicles per day, with summer peak volumes reaching 18,000 vehicles per day. The river bridge on the left side of the screen, which crosses the main river channel, and the relief structure on the right were located approximately 600 feet from each other. They were constructed in a roadway fill section that crosses the wide Bear Camp River floodplain when New Hampshire 16 was realigned in 1955. To provide some additional orientation to the project site, north is to the right of the page. The Bear Camp River flows east down the page towards Ossipee Lake, and the area downstream of the bridges contains a large wetland system and sensitive environmental communities. Aerial utility lines are located along the east side of the road. There are businesses located on the west side of the roadway at each end of the floodplain, and there is a residential neighborhood located within the floodplain just west of the road. This is the former Bear Camp River Bridge. It was a 392-foot long, 5-span steel I-beam structure. As you can see in the picture, the end spans and most of spans 2 and 4 are over dry land under typical flow conditions. This area begins to flood after heavy rainfall events. This is the former Bear Camp River Relief Bridge. It was a 168-foot long, 4-span steel I-beam structure. This bridge is located on the northern side of the floodplain to provide additional hydraulic capacity at the crossing during flood events. Due to the significance of the roadway as a major north-south corridor, the following design considerations were identified as the design team began working on traffic control for the project. The design speed needed to remain at 45 miles per hour. The roadway elevation needed to be maintained above the 100-year flood elevation, and any temporary bridges would need to match the spans of the existing bridges due to their location within the floodway and the length of time that they would be in place. And, as always, the design would seek to minimize the impacts to abutting properties and the environment. The initial alternatives analysis considered the construction of a roadway diversion with temporary bridges to either the east or west side of the existing road. These alternatives required significant fill in the floodway to keep the road above the 100-year flood elevation, and also long, costly temporary bridges. To minimize the costs associated with constructing such an extensive diversion, the team evaluated shifting the permanent alignment of New Hampshire Route 16. Again, both eastern and western alignments were considered. We even considered building one bridge using a diversion and the other on a new alignment. Based upon the site constraints, each of these new alignments presented challenges like difficult geometry, significant impacts to the sensitive wetland area, or impacts to the businesses and residences. This is where the idea of using slide-in bridge construction was born. This technique allowed the bridges to be replaced on the existing roadway alignment, which was already in the best location, without the cost of building the diversion and temporary bridges. This table summarizes the initial comparison of all 6 alternatives, showing an estimated savings of $2 million using slide-in bridge construction over the baseline of building a diversion with the temporary bridges. In addition to minimizing the construction duration and impacts to traffic, the environment, and abutting properties, Selecting the slide-in bridge alternative also saved money and provided a benefit for New Hampshire DOT, as we could gain experience with this technique in a low-risk location before using it elsewhere in the state. Now, here to talk about some of the design considerations is Sam White, one of the design engineers from McFarland Johnson.
Thank you, Jennifer. There were three primary design considerations at the forefront of the design and detailing of the bridges. These considerations were the accelerated closure duration, movement of the bridge both horizontally and vertically, and constraints associated with the existing bridge. These design considerations and concepts applied to both the river bridge and the relief area bridge. The scheduled roadway closure duration was 84 hours. With this condensed construction window, design concepts and detailing that would expedite construction were needed. Precast elements were utilized for components that could not be installed before the closure or slid in as part of the bridge slide. As an example, these photos show a unique precast wing wall element that could be placed on the pre-installed abutments during the closure. Sliding the bridge horizontally required special consideration for both vertical and lateral foundation design loading. This photo shows the varying loading condition created on the foundation by sliding the bridge. To limit potential lateral forces transmitted to the foundations, a maximum static friction value of 15% for the slide system was included in the contract. Once the lateral bridge slide was complete, the bridge needed to be lifted vertically to remove the slide system components and then be lowered onto its final bearings. This photo highlights the details developed to accommodate vertically moving the bridge, including a recessed shelf in front of the bearings, an additional bearing stiffener, and varying sole plate thicknesses to accommodate the cross slope. The new bridge foundations needed to be installed prior to the roadway closure. Since the location of the new bridge coincides with the existing, the new foundations needed to be detailed around the existing bridge. The photos below show how the existing bridge dictated the location of the proposed piles. The piles were installed through the existing deck and had to be spaced around the existing beams. The existing bridge low chord elevation controlled the beam seat elevation of the proposed foundations. This photo shows the importance of double and triple checking elevations during design. This image of the relief bridge, which is just prior to the slide, further highlights the site constraints with the existing bridge. The green rectangles shown are the location of the existing foundations. The proposed foundations were located to avoid the existing foundations and maintain a similar hydraulic opening as the existing. While only the condition at the relief bridge is shown, similar considerations were required for the river bridge. Many of the design challenges, concepts, and details discussed will be further illustrated in the next construction portion of this presentation. Since it is his favorite part of the project, Jim will now present the construction portion of the show.
This provides a nice overview of the Bear Camp River site. In this picture, the abutment A and Pier 1 temporary supports are in, and it looks like they're driving piles for the Pier 2 temporary support. Notice that the utilities have been moved back. In this picture, one might wonder why, but later in the presentation you'll see that we used most of the available space. This shows the layout of the new substructures relative to the old substructures. The old substructures are the battered pile bents, and the new substructures are the single row of vertical piles. We started by driving the piles that were outside or next to the existing bridge. This slide shows the driving of one of the outboard piles at the relief bridge. Pier piles were 30-inch diameter with 1-inch wall thickness, and abutment piles were 24-inch diameter with 3/4-inch wall thickness. On the river bridge, the abutments were on 8 HP 14 by 89 H piles. The relief bridge piles range from 180 to 200 feet, and the river bridge piles were in the 90 to 150 foot range. Next, we had to drive the piles through the deck. This was cause for a lot of discussion during design. The thought of cutting holes in a red-listed bridge deck and shaking and pounding piles through it was a little disconcerting. Each pier had 4 piles, 2 that were outboard of the deck and 2 that went through it. First, the contractor cut and removed a square of pavement. Next, a round hole was cut and chopped through the concrete deck. 1-inch thick steel plates were made to bolt over the holes. These were removed to drive the piles and then replaced once the pile was through. The contractor made a steel guide to more accurately hold the piles. There was also a frame at ground level to hold the pile in position during driving. On the first one, the contractor thought it would be a nice gesture to use some drop-in anchor bolts to hold the guide, but they just rattled loose and they proved to be unnecessary. Due to the length of the piles, multiple 60-foot piles were welded together. Plywood shields were made to keep passerbys from burning their eyes watching the welding. Despite all the concern about vibrations from pile driving damaging the bridge, what we found was that vibration from pile driving was felt significantly less than vehicles, especially trucks going across the bridge. Due to the theoretical 40-foot scour depth, the plans called for the top 60 feet of the pile to be filled with a rebar cage and concrete. In many cases, a soil plug formed when driving the open-ended piles, but in a few cases, some material had to be removed by augering. This is a rebar cage being lowered into a pile on the relief bridge. Here are some completed piles at the relief bridge, and the earth has been prepped for pier formwork. This is some pier formwork and shows how little headroom there was. Pumping the concrete for the piers and abutments wasn't easy with so little headroom. The pump clogged on at least half of these placements. And here's a partially stripped completed pier at the relief bridge. This is how the contractor elected to do the abutments that were not under the existing bridge. This happens to be at abutment B of the relief bridge. The plans had a design for precasting the abutments with the intention of installing them during the slide weekend or perhaps during one of the periods when alternating one-way traffic was permissible and then bearing them. The contractor originally intended to do it that way, but then when they were driving the sheet piles for the cofferdams, the superintendent, who knew they had some concrete slabs that could be used to make a roof for the cofferdam, proposed casting the abutments in place in this cofferdam with a roof. This shows a couple workers tying the rebar cage with traffic flowing unimpeded above them. Here's the top of a completed abutment. Notice that there's no step bridge seats, and there's also a jacking shelf to be used for jacking the bridge down once it's slid into place. Also visible are the sleeves for the anchor bolts and the grout tubes for grouting them in. On both these bridges, the contractor built the bridge on a slide beam or pole beam. Once the new permanent piers and abutments were done, it was time to build the temporary piers and abutments and new superstructure. Here's a picture of a slide beam sitting on a temporary abutment. Notice the C-channel on top of the temporary abutment that will act as a guide for the rollers. Here you can see a girder sitting on top of a block of wood that is sitting on the pole beam. The temporary block of wood takes the place of the permanent bridge shoe. Notice the green rectangular roller blocks under the slide beam. These are the Hillman rollers. Also note the marks on the slide channel. These will be used during the slide to make sure that the bridge is moving equally at each pier and abutment. This is a close-up of a Hillman roller.
So this is a Hillman roller upside down. As it rolls, the rolls are attached to the chain. They're actually traveling around a centerpiece of steel supporting the load.
The manufacturer says that the rollers have around 2% friction. When we did the test slide, I did a calculation using the jack pressures that indicated we were getting around 1.8. Here's a quick shot of the structural steel on top of the pole beam. This shows the back wall forming, and you can see the bunks are laid out on the girders for forming the deck. Remember that this is an integral abutment bridge, so the back wall is formed as part of the deck. Same as any bridge, you should always dry run the screed over the deck to check for proper depth, cross slope, and rebar clearance before placing the concrete. Here's an overview of the on-site precasting yard for the abutment wings, approach slabs, and sleeper slabs. The long, narrow form on the left is for a sleeper slab, and the square with some epoxy-coated rebar in it is half of an approach slab. This is a partially stripped wing wall. Once all the pieces were made and all the suppliers, shifts of people, and subcontractors were scheduled, and the seemingly hundreds of detour signs installed, stakeholder meetings held, and the public notifications were made, the big weekend arrives and begins with demolition of the old bridge. This is by far the most time-consuming and dangerous part of the whole weekend. It is the riskiest part, not only in terms of worker safety, but also in terms of time delays. The deck was first saw cut and then removed by excavators with slab grab buckets. The excavators would put the slabs on dunnage behind them, and a loader with forks would pick them up and haul them off the bridge, stack them up on the sides of the roadway approaches where they would eventually be loaded onto trailers and taken away. There were 2 excavators working away from each other towards opposite ends. This is a picturesque scene during the first night of the river bridge slide. The picture has a nice effect, but for the guys doing the cutting and those of us watching the